Okay, 10 a.m. Time for Rob 101. We start week 3. University's still open. I'm still happy about that. I know I keep talking about it. You guys think you must be obsessed. But yeah, I was afraid I'd be sitting in my office or something all by myself trying to teach Rob 101. And we don't have a lot of people showing up, but it's better than 0 people showing up, let me tell you. Okay, so let's make the connections with what we were doing last time. We had introduced the notion of a triangular matrix. So these, for us, right now, we're only defining it in the case of square matrices. So we have a diagonal. And for lower triangular, we want all of the terms above the diagonal to be 0. And for upper triangular, it's just the opposite. And so whenever A is triangular, its determinant is super easy to assess. You just take the product of the terms on the diagonal. And since solvability in terms of uniqueness is determined by whether the determinant of A is equal to 0 or not equal to 0, you don't even need to multiply them out. You just check if there's a 0 element on the diagonal or there is not. So that simplifies everything. So if we have lower triangular and the determinant is not equal to 0, that means when we can use forward substitution, all of the coefficients that we're dividing by here, the A11, the A22, the ANN, those are the elements of the diagonal of the A matrix, and hence determinant of A not equal to 0 means forward substitution works, and then it becomes a triviality to solve for x1. You plug it in, then you solve for x2, then you plug in x1 and x2, etc., until at the very end you've already solved for x1, x2 up to xn minus 1, and then you get xn. So it just cascades through, and this is called forward substitution. And in Julia, you should start looking at that. You will solve a 100 by 100 system of equations. So we will first have you do a 10 by 10. Well, no, we'll do 3 by 3 or 4 by 4, and then we do a 5 by 5, and then we do a 10 by 10 where we do kind of fake looping, where you'll just run the cell over and over and copy the result and put it in, and then run the cell again and copy it. So it's kind of like looping, except you manually run the process over and over. But that'll get the idea ingrained, and you wouldn't want to run it over and over for 1,000 by 1,000. Okay, so we won't, but we'll have you do it in a loop for 100 by 100. Similarly, so the opposite of lower triangular is upper triangular. And if we have upper triangular and the determinant not equal to 0, then we can use back substitution, also called backward substitution. And the key thing is you start at the bottom and work your way up. So you go bottom to top. It's the exact same process. And the elements you're dividing by are the elements of the diagonal of A. So determinant not equal to 0 means there is not a 0 on the diagonal, and hence you'll never divide by 0, and everything works out. So triangular matrices, that seems pretty solid for everyone. Just need a little practice maybe, but it's almost mechanical. And that's why we can implement it on a computer. Okay, so now we're upping our level of abstraction. We're really starting to do a little bit of algebra. This is matrix algebra. And so when you're doing algebra, you do addition of real numbers, you do multiplication of real numbers, and once you know how to do multiplication, you can do powers and things like that. So we're now doing the multiplication part of matrices. And the first matrices we started with, and this is where we left off on Friday, is we took a 1 by k row vector, so that's a 1 by k matrix, and we took a k by 1 column vector, so that's a k by 1 matrix, and we defined the product of a row vector and a column vector to be the sum of the product of the elements. You take A1 times B1, and you add it to A2 times B2, dot, 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 AK times BK. So you just add all those up. And so the compact notation is just to write the sum as I equals 1 to K, where I is the index, but that just means you sum everything up. So row vector times a column vector, when they have the same elements, that gives you a scalar. It's just a real number, just a scalar. Well, I want to pause right here. Are there any questions on how to multiply a row vector and a column vector? Check the chat, anything? Because if you can do that, you can multiply matrices, okay? This is the basic operation. It all boils down, the standard way of doing matrix multiplication is taking rows times columns. You just have to pick out the right rows and the right columns. So if you have no trouble with this, the rest of it is bookkeeping. So I want to make sure we can do row times column. They should have the same size, or we can't do it. Okay. I have a feeling people get it. Okay, so let's talk about partitioning a matrix into rows and columns. And this will allow us to break down the product into that simple operation. Okay, so I'll take A, it'll have 2 columns and 3 rows. So this is a 3 by 2 matrix. So the rows probably exactly what you think. Here's a row. Here's a row. Here's a row. Come on. Boom. We'll delete that one. Come on, move up. Well, anyway, who cares? Leave it like that. So these are the rows of A. And we could call that A row 1, A row 2, A row 3. So that's how we partition A into rows, just like we would in a spreadsheet. Good with that? Okay, let's rewrite A 1, 3, 5, 2, 4, 6. And I'll try to do better. Here are the columns. Okay, and we'll call this, for example, A column 1, A column 2. So we can just take any matrix, we can look at individual elements, but we can also group them together and get all the elements in the different rows and all the elements in the different columns. Okay, so let me do one of my paste in. Hopefully the file is there. Image. Equations. Oops, I need to go up one. General. Okay. Okay, so if you're typing, you need to mute your mic because we hear the typing. Okay? So if we have to, Tribby's going to go on and just kill your mic there. And the typing wasn't fast enough to be Monty's, was it? Maybe, you're not sure? So just teasing Monty. So here's a more general matrix that has n rows and m columns, and there's the breakup of the matrix into its columns. So here's a column, here's a column, here's another column. So it would have m columns, and they're all indicated here. And so we should be able to do the similar thing for rows. Whoops, hopefully it's in there. Insert image file. Bingo. General form column, row multiplication. Rows of A, there we go. Come on. Shrink enough to fit in here. Okay. What are you? We'll delete you, whatever you are. Get you out of the way. And so we can also take A and then get the individual rows, just like we did on that small example. Okay, so if you can multiply rows times columns, just like we looked at, that's how we're going to do matrix multiplication. So let's lay that out. So, bingo, go away. So this is standard matrix multiplication. So you take rows times columns. Okay, so let's first talk about sizes. So when we did the multiplication of a row vector and a column vector, we emphasized they had to have the same size. So we're going to look at A times B. So we're going to let A and B be matrices. Okay, and then we're going to suppose that A is n by k, right? So that means n rows and k columns. And we're going to also suppose something on B. B has to be k by m. So that's k rows and m columns. Okay, so before, when we multiplied a row vector times a column vector, we needed, A had one row, but it had to have the same number of elements, so those were elements in the column. And B, when we looked at it, it had to have the same number of rows as A did columns, and so that's what we have here. This is number of columns of A. This is the number of rows of B. So that's the key ingredient for being able to multiply them. Okay, so we just want to get this fixed in our minds, and then we'll look at the formulas. Then the product, A dot B, makes sense. And results in an n by m matrix. Okay, so once again, the key thing here, number of columns of A has to match the number of rows of B. Number of columns of A has to be the same as the number of rows of B. Okay, so here, N, M, and K are arbitrary integers greater than or equal to 1. We don't want 0 rows or 0 columns. Than or equal to 1. Okay, so that's just the dimension thing. We need certain sizes on the matrices to make the product make sense. And that's just like when we had the rows and the columns, we needed the length of the row vector and the length of the column vector to be the same. So this is a very similar thing. So let's just do a few examples. 1, 2, 4. Let's see how many I need. Okay, suppose we have a 3 by 3 matrix, and we multiply it by a 3 by 7 matrix. What should that equal? Okay, and then we just put a few more and we'll do them. And so I'm going to stop writing matrix because it takes too much space. Okay. Let's say 5 by 5 times a 5 by 5. Why not? 3 by 4 times a 4 by 2 equals. And then I'm going to do one more here. Let's see. Let's do a 4 by 5 times a 4 by 4. Okay, so I just want to get the sizes of these matrices. There are no typos. Hold those thoughts. Okay, so if we take n by k times a k by m, we get n by m. So 3 by 3 times a 3 by 7 gives us, once again, we get a 9 by 21, right? No. So the 3 and the 3 are the same. So this 3 and that 3 are the same, so we can form the product, and then the matrix becomes 3 by 7, okay? 3 by 7. Very good. So we do a row vector, 1 row and n columns, times a column vector, which has n rows and 1 column, we get a 1 by 1. Yep. Okay. Key thing, the two n's are the same. Here we have two square matrices, a 5 by 5 times a 5 by 5. We recover a 5 by 5. Okay, now we get a 3 by 4 matrix, we multiply it by a 4 by 2. Once again, we see the number of columns of the first matrix is the same as the number of rows. That's the magic thing. And then 3 by 2. So we get a 3 by 2 matrix. And here we have 5 columns, 4 rows. 5 is different than 4, so the multiplication does not make sense, okay? So this is undefined. Okay, so we only know how to multiply matrices when the one on the left, its number of columns is equal to the number of rows of the matrix that follows it. That's the key part. I see a few of you like not too excited about this. That's okay. It's the first thing you always check when you're doing matrices though, okay? So, and it's very easy when you're generating matrices in a problem that you, if you don't check things carefully, you'll mess this up, and then Julia or MATLAB or any other program you're using will simply go berserk, okay? It will tell you, no. Okay, so we'll just do some examples of multiplication, and then we'll write down the general formula, okay? So I'm going to define a matrix, A times B. I'm going to give you A and B. Then I'm going to define the matrix C. So this means C is by definition equal to A times B. So we've talked about this a little bit. The side of the equal signs where you put the colon means this is the new element, and A and B, you should know them. And I will give you A and B, and we will, from that, compute C. And that's the same thing here. So the side of the equal sign where you put the colon, that's the element that is new here and being defined. If you don't like that notation, just remove the colon and just say C equals A times B, and life is good, okay? So, but this is how mathematicians keep track of knowing, oh, I should go further up in the paper and find that symbol where it's already defined. It's like you reading a sentence and you see the word it. You know, if it's a good writer, you don't read further down to figure out what it is, though about half of people below that, it should be defined previously in the paragraph. So that's what's going on here. Okay. Yeah, I know. I shouldn't be making connections to English, right? Here's A. And those funny numbers are 3 and 4. Let's make them a little bit clearer. 3, 4. So I'm going to write that as A row 1, A row 2. Okay. So 1, 3, 2, 4. Here's a row. Here's a row. Whoops. Here's B, and I'm going to keep it simple. It's going to have one column. Okay, so that equals B1 column. Since there aren't two, I won't break it up. It's pretty clear that B1 column is 5 and 6. Okay, so here's the definition of the product. A, B matrix product, which I'm going to write as A1 row, A2 row, dot, B1 column. Okay, so let's look at the sizes here. I'll let you catch up on the writing. But this is 2 by 2, and this is 2 by 1. So when I multiply them out, the size of the answer is supposed to be 2 by 1. So I have the same number of columns in A as I do rows in B, so this is going to make sense. And the size of that should be another 2 by 1 vector. And it will be, okay. The first element is A1 row times B1 column. And the second element in it is A2 row times B1 column. Okay, so this is 2 by 1. 2 by 2, 2 by 1. This is our matrix C. The product, it's 2 by 1. Do we know that it's 2 by 1? Well, A1 row. Okay, there it is. It has 2 elements. B1 column. There it is. It has 2 elements. When I multiply a row vector times a column vector, I get a scalar. So this is a scalar, the first entry. This is a scalar. Similarly, I do A2 row times B1 column. I get a scalar, so that's 2 scalars, so that's a 2 by 1 matrix. Okay, what are its elements? Okay, so this is really working it out in a way that you will never do this much detail ever again. But, oh yeah, I've got them written over here on the side. So this is 1, 3, and this is 5, 6. So this is equal to 1 times 5 plus 3 times 6, and that's 18 plus 5, that is 23 on Monday. Tuesday, I'll get a different answer. Okay? So that's the first entry. And then A2 row times B1 column is 2, 4, 5, 6. And so we multiply the 2 times the 5, and we add that to the 4 times the 6. 24 and 10, we get 34. Okay, so then A times B, which is 1, 2, 3, 4, times 5, 6, is 23 and 34. Tedious enough for you? Yeah, okay. So the above is how a computer does matrix multiplication, okay? It's extremely mechanical. I'll give you the human view of that in just a second, but we'll see if there are questions on how the computer thinks about matrix multiplication. Next, a more human view, okay? Boop, come on, come on. Thank you. Okay, computer. First thing we do, we extract out all of the rows of A. Next thing we do, we extract out all of the columns of B. In this case, we only had one. And then we start multiplying the rows times the columns and filling them in. Okay, we just extract them out, form those products. They're row times column products, and we just stick them in the right entries. Okay, so it's going to be doing this individual computation, and then it knows to stick them into the first entry of C and the second entry of C. That's the computer way. Okay. This is what I and everybody else does. Okay, it's 1, 2, 3, 4 times 5, 6, okay? Fine. We will not draw these boxes when we're doing it, but this is what we're doing. We're going the 1 times the 5, and then the 3 times the 6. So we're moving our fingers across to keep track of the entries, because when there's 4 or 5 of them, it's real easy to all of a sudden you're multiplying the third entry of the row times the fourth entry in the column and you get it wrong, right? So you're just moving your fingers across, okay? And since it's hard for me to show that on this tablet, oh, come on. But we just write this down, and then we go, whoop, okay? We go just quickly, 1 times 5 plus 3 times 6, and we just add those up in our head and we write it in, okay? And then we go 2 times 5 plus 4 times 6, and we just add those up in our head, and that's the 18, that's still 23, and this is still 34. Okay, so we don't do any calculations on the side or anything, okay? Am I making any sense, since I can't go to the whiteboard because the students in the Zoom land, you guys cannot see me doing that, but I think you can see me doing this, where I'm mentally going 1 times the first entry of B, 3 times the next one, and if A had more columns, this thing had more rows. I'm just multiplying them, and I'm probably doing the addition mentally instead of writing down the numbers, okay? That's what we do. We get it right about 8 times out of 9, okay? So that's fine. Okay, let's do another one, just more human way as well. What if A is 1, 2, 3, 4, 5, 6? I'm sure you love my very imaginative use of numbers. And B is x1 and x2. Why not? Okay. This thing has 3 rows and 2 columns. This has 2 rows and 1 column. So that's going to work, and we're going to get a 3 by 1 matrix. So a column vector, right? Well, what is A dot B equal to then? If we do the human way, we just go 1 times the x1 plus 4 times the x2. Okay, so x1 plus 4x2. Human way, we go 2 times the x1 plus 5 times the x2. 2x1 plus 5x2. Human way, we just go 3 times the x1 plus 6 times the x2. 3x1 plus 6, well, fortunately you know what those are, and you don't have to decipher them too much from what I've written down here. But, okay, so that's the essence of matrix multiplication. You're always, always, always just doing rows of A, and then so far we've only done 1 column, and now we're going to do 3, 4, whatever we need. Pause for questions. Am I presenting it too clearly so that nobody wants to even ask? Okay, Trivia, I got to mess something up here. Okay, so let me go for it. So I'll do the general definition. Okay, so we'll say A is N by K. Ooh. Okay. So I'm going to write that as A1 row dot 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 AI row dot dot dot. Oops, didn't quite get it down far enough. AN row. Okay. How many, I'm going to let you get that written down. So if I look at AI row, what is the size of AI row? Well, it's a row, so it only has 1 row, okay? But how many columns does it have? 8, did I hear? K, okay? So the answer is K, okay? Has the same number of columns as A does. A has K columns, and that's what we have here. Okay? So let's write down B, and it needs to have K rows, or we cannot define the multiplication, and we'll say it has M columns. Okay, so I'll just write this as B column 1 dot 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 B sub j column dot 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 B sub k, M, what am I doing here? K. It has M columns. Okay, so the generic column, B sub j, has the same number of rows as B, and it has 1 column, because it is a column. That's the size of it. Okay, so I'm going to define C by definition of A dot B, and I'm going to define for you the ij entry of C. So C is a matrix. I'm going to give you the entry on the ith row and the jth column. Its ith row is the ith row of A times the jth column of B. So this is the ij element, well, looks like I minus j. Ij element of C. Okay, you don't need to copy this in your notes, but it'll be there, right? So C is C11, C12, dot, 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 and C is, let's see, N by M, so this will be C1M, C21, C22, dot, 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 C2M, dot, 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 CN1, CN2, dot, 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 CNM, okay? So I'm just giving you the ij entry. So everything boils down to rows of A times columns of B. And if you want the 2-2 entry of C, it will be the second row of A times the second column of B. If you wanted the C3-4 entry, it would be the third row of A times the fourth column of B. It's very, very mechanical. Okay, you break A up, you take the ith row of A times the jth column of B, and you get the ij entry of C. So plug in I, plug in J. First row, first column, C11. First row, second column, C12. Nth row, first column, CN1. 27th row, 34th column, we get C2734, if those were the numbers I said. Okay, so that's how you do it, okay? Row times column, row times column. Am I beating this horse to dead, or is it just helping just ingrain it where it's a reflex? That's what I'm trying to do. I'm trying to imprint this so it's a reflex. Ith row, jth column, ij element of the product, okay? That's what I'm trying to imprint in our brains here. So 1, 2, 3, 4 again. Okay. A1 row, A2 row. B, I'll make sure it has at least 2 columns. 5, 6, and I'll surprise you, -2 and 1 instead of 7 and 8, okay? B1 column, B2 column. So A times B, I'm going to write this out. 1, 2, 3, 4, 5, -2, 6, 1. And hopefully I'll write small enough that this will work, okay? So let's identify rows of A, columns of B. Okay, the 1-1 entry of the product. We take the product of the first row, whoops, you get out of there. take the product of the first row and the first column. So this is 1 times 5 plus 2 times 6, okay? Normally we just add those up in our head. We'd go 1 times 5 is 5, 2 and 6 is 12, so that's 17. We wouldn't write it out. But so you can go back to your notes and figure out where the 17 came from. I'm gonna write it all down, okay? It hurts me too to do that. Now, I don't know, let's do the first row and the second column of C. So we have, I'm gonna have to squeeze this in, we have 1 times minus 2 plus 2 times 1. 1, we go 1 times minus 2 plus 2 times 1. So that's 0. Let's get the second row, first column of the product. So it's 3 times 5 plus 4 times 6. What are you doing this today to me? Plus 4 times 6. So 3 times 5 is 15, 4 times 6, 24, that's 39, okay? So normally we wouldn't write all this stuff out. We just write down a number. If you get it wrong, what the heck? Half a point on homework, okay? But if you're doing it on the computer, you don't get it wrong. And then the last, second row, second column, 3 times minus 2 plus 4 times 1. Okay, 5 was 17, minus 2 plus 2, 0, 15, 24, 39, and then minus 6 plus 4, minus 2. That's the product. Hey, the same numbers I have here. I'm always amazed when that happens. How's that? Pretty good? Now these two matrices, we can also multiply B times A, and I want to show something really important, and we'll end on that. So this is 2 by 2, that's 2 by 2. So A times B makes sense, but B times A also makes sense. We can flip the order. Okay, we'll do that one more quickly. Okay. Okay, so B is 5, 6, minus 2, 1, multiplied by A, which is 1, 2, 3, 4. We'll quickly get the rows of the first matrix and the columns of the second matrix. We'll get the columns of the second matrix. Okay? So this time, let's just write down the numbers instead of writing down all of the multiplications, okay? So, first entry of the row 1, column 1, we have 5 times 1, 5 minus 2 times 3, minus 6, so this is minus 1. Next one, we have 5 times 2 is 10, minus 2 times 8, so that's 2. Next one, 6 times 1 is 6, plus 1 times 3, that's 9. Next one, 6 times 2 is 12, plus 1 times 4, 16. So that's how you'll normally do it, okay? And you won't even draw boxes around it. And if it has 2 elements, you don't even need to run your finger, but if it's 3 or 4 elements, you'll just run your finger, okay? Now, This is A times B, and this is B times A. Are they equal? Okay, now when you do pi times square root of 2, or you do square root of 2 times pi, are they equal? Yes. Scalars commute. It doesn't matter the order. Matrices, order matters. Super important, whether it's A times B or B times A. Okay, so I'll write that down, but order matters. But I've run out of time, so because I will respect the 50 minutes of class. Okay, guys? Super. Tribby will do a recitation. If you have questions, please send them in to Tribby. It will help her be more relevant. If you're having trouble navigating the Canvas page to find homeworks, whether it's the drill problems or the Julia problems, let us know, and Tribby can walk you through how you do that, where the submissions are. I'm going to be posting some good practice on Gradescope for the scans and some less good practices that we've seen, but that's all part of the normal learning process. Nobody's getting points taken off because they didn't scan in a way that makes it easy to grade, okay? We're just going to give you hints of how you can make it a little bit easier on us. So that's great, people. Thank you.